Hello, this is Miss Moore, and today during chemistry we're going to discuss types of atomic bonds. Today's essential questions: what are the properties of the different bond types? Probably a better way to say that is, what are the types of properties of molecules formed by different bond types? Anyway, we will start with ionic bonds. So, definition of an ionic bond. An ionic bond is an electrostatic force that holds ions together in an ionic compound. So, electrostatic force, that just means the attraction between positives and negatives. In this case, positive ions or cations with negative ions or anions. Okay, so ionic bonds are made up of a metal, which is a cation, and a nonmetal anion. Another way to think of ionic bonds is that they're made up of atoms with a large electronegativity difference, which makes sense, right? Because metals have a very low electronegativity and nonmetals have a high electronegativity, which allows the nonmetals to steal from the metals, which is written here. The more electronegative nonmetal steals let's change that, an electron from the less electronegative metal. All right, now we need to talk about something titled lattice energy in terms of ionic bonds. So, the lattice energy is the energy required to separate 1 mole of an ionic solid compound into a gaseous ions. So what you want to think of is lattice energy is really the energy needed to break apart an ionic compound, so to break those ionic bonds. And the larger the lattice energy, the more stable the ionic solid, because it's harder to break it apart. And the value, or you could think of it as the strength of the lattice energy, depends on 2 different things. The charge of the ions, and not whether or not they have a charge, but how big the charge. So, for example, 2 plus versus 1 plus. Okay? And the distance between them, which is related to the size of the ion. So not really atomic radii. Let's change that to ionic radii. And all of this, the charge of the ions and the size, the distance between the ions, should be very reminiscent of Coulomb's law, where F, which is the force, we could also call that energy if we wanted to. The force holding together the molecule or the ionic compound, or the energy needed to break it apart, equals some constant times charge 1, that's the Q, and charge 2. In this case, you can think of these as the ions, right? So this one, in theory, could be the positive ion times the negative ion, or vice versa, divided by the radius, or the distance between the 2 ions. Right. Let's try to predict lattice energy of 2 different ionic compounds. So, question is, which of the following would have the greatest lattice energy? Magnesium chloride or sodium chloride? Keeping in mind Coulomb's law, and let me put a little portion of the periodic table there so we can kind of think this through. So again, Coulomb's law is force or energy equals some constant times the charge of, let's say this is the cation, and times the charge of the anion divided by the distance between them. Again, and that's related to distance here. Distance between them, which is related to the size of the ion. Okay? All right. So, first of all, we'll note that we have chlorine in both of these compounds, so we can ignore that as far as looking at which has the greatest lattice energy, because since chlorine's the same in both of them, it isn't really going to play a role. So we will look at magnesium and we will look at sodium. So what do we see here? Well, the charge on a sodium ion is a 1 plus, and the charge on a magnesium is a 2 plus. So the charges are different. The size is also slightly different, with sodium being slightly larger, but because they're right next to each other, the size is going to have very small impact. So let's ignore the R for now. We just need to look at the charge. Well, sodium has the bigger charge, right? So when you multiply this all out, you're going to end up with a bigger force or energy, which means that MgCl2 has the greatest lattice energy. Okay, let's try one more before we're moving on. So this time, which of the following would have the greatest lattice energy, sodium chloride or sodium bromide? So let's put our little periodic table back, portion of it, and our Coulomb's law again, force or energy equals some sort of constant. Some sort of constant times the charge of the cation times the charge of the anion divided by the distance between them, which again has to do with the size of the atom. All right, so Na is in both of these, so we can ignore the Na for now because it's not going to have an impact. We just need to look at the anions, chlorine and bromine. All right, well, let's start with the charges. Bromine has a charge of Br1 minus, and chlorine has a charge of Cl1 minus. All right, so the charges are not going to make an impact on which has the greatest lattice energy. So what about the size of the atom? Well, or ion. Chlorine is in energy level 3, which means it has 3 shells, right? And bromine has 4, which would mean bromine is significantly larger than chlorine, okay? Which would mean for bromine, the R would be a bigger number. Okay, so if we are dividing some number by a larger number, that's going to make the E smaller. So that means bromine has less, the compound with bromine and NaBr has less lattice energy, which means which of the following has the greatest lattice energy would be sodium chloride. Okay? So that's it for lattice energy. Let's move on to some properties of ionic compounds. Ionic bonds are very, very strong bonds. They are usually solids at room temperature. Think sodium chloride, salt. It's a solid at room temperature, right? They have very, very high melting and boiling points. Trying to melt salt, for example, is an almost futile effort. They're soluble in water. And what does soluble mean? It means it can dissolve. In fact, they dissolve very, very readily in water. And they conduct electricity in, this is important, the liquid and aqueous states. Aqueous, what does aqueous mean? It means dissolved in water. Okay, so they conduct electricity very well in both the liquid and the aqueous states. They do not conduct electricity in the solid state. Okay, so you really, really, really need to know the properties of ionic compounds. All right, on to covalent bonds. So what is a covalent bond? In a covalent bond, it's a bond in which 2 electrons are shared shared by two atoms, which is very different than the ionic bond, right? With the ionic bond, one atom steals an electron, so to speak, from another atom, making them both ions, and then they're joined together because they're attracted by those opposite charges. With a covalent bond, there's no electron stealing, they're sharing, although not always equally. Made up of two or more nonmetals, they're made up of atoms with small or no difference in electronegativity, which would make sense. Nonmetals are, in general, more electronegative than metals, and covalent bonds are made up of nonmetals, right? It also makes sense because electronegativity is the ability to steal an electron. And so if you have two strong atoms, they're not going to be able to steal. So they're going to end up both holding on to the same electron. Think of it almost like a tug of war. They're both holding on to the same electron. All right, and then a few more properties of covalent bonds. Covalent bond length. The bond length is basically the distance between the nuclei of two covalently bonded atoms. So how far apart are they? Okay, shorter bonds are more stable than longer bonds. Okay, so when do you have short or long bonds? Well, onward. That has to do with how many bonds there are. A single bond is two electrons, or one pair of electrons is shared by two atoms, and these are the longest bonds. So single bonds are weaker than, let's say, double bonds. Double bonds is four electrons, or two pairs are shared by two atoms. Each atom contributing two electrons. And then you have triple bonds, in which case each atom is contributing three electrons. So 6 electrons, or 3 pairs, are shared by two atoms, and this is the shortest bond length, which means of the covalent bond, it is also the strongest or most stable. And on to properties of covalent bonds. Covalent bonds are weaker bonds than ionic, and they are often liquids or gases at room temperature. Think water. They have low melting and boiling points, much lower than ionic bonds. It's very easy to melt most covalent compounds. Sugar is an example. You can melt sugar. It looks a lot like salt. Salt is an ionic compound. Sugar is a covalent compound, and it melts fairly easily. It's insoluble, often insoluble in water. Not always, but often, meaning it's more difficult to dissolve. Again, think sugar and salt. While it's true that sugar will dissolve in water, the same amount of sugar versus same amount of salt, it'll be a lot easier to dissolve the salt. It's very, very soluble in water, where sugar is not nearly as soluble, although it is. Covalent compounds do not conduct electricity, not in the solid, liquid, or gaseous, or aqueous states. They just absolutely do not connect electricity. So they are often used as insulators. Okay, the insulators don't conduct electricity. Okay, and so often covalent compounds are used as insulators. Okay, next we need to talk about electronegativity and bond type. How do you tell when something's ionic or covalent? It all has to do with electronegativity. If two bonded atoms have the same or similar electronegativities, the bonds will be what we call non-polar covalent. That means that the electrons are equally shared. Let's go back for a second. Often, just a quick and dirty way to check if something's nonpolar covalent, if they're really, really near each other on the periodic table, they are likely going to be nonpolar covalent. Think that if they're touching on the periodic table, there's a really good chance that it's nonpolar covalent. If two bonded atoms have different electronegativities, the shared electrons will be shared unequally, with electrons spending more time near the more electronegative atom. And the greater the difference in the electronegativity, the more and more the bond will resemble an ionic bond, up until the point where it actually is an ionic bond. Okay, so bonds are actually more graded than strictly delineated between ionic and covalent. Okay, so something that's really, really electronegative may be ionic, but maybe just slight, or maybe really, really polar covalent. So the electronegative difference is great enough, the electron will then transfer to the more electronegative atom, resulting in ion formation and then an ionic bond. And on to metallic bonds. Metallic bonds are a closely packed lattice of positive metal atoms, they're kind of like ions, surrounded by a sea of moving electrons. So very different than both the covalent and the ionic. You've got all these metals, it's going to be just with metals. They're all packed close together and their electrons are kind of flowing around. And that all those free electrons kind of flowing around make them really, really good conductors of electricity. Anyway, we'll get there to that in a minute. All right, so metallic bonds are always made of just simply metal atoms. And a few properties of metals is that they are solids at room temperature. They have extremely high melting and boiling points. They are insoluble or not dissolvable in water. They are super good conductors of heat and electricity. And this is at any phase. So solid and liquid. Remember, for ionic compounds, even though they're good conductors of electricity, they conduct electricity only in a liquid and aqueous state. Metals, on the other hand, solid, really good conductors of electricity as well as in the liquid state. And they are ductile and malleable. So that means that you can bend them and twist them, you can hammer them down flat without breaking them, which is completely not true of ionic and covalent compounds. And the last major topic for today are types of crystals. Okay, so types of solids. And we'll start with ionic crystals. Ionic crystals are closely packed spheres of positive cations and negative anions. The normally larger anions are packed closely together, with the smaller cations fitting into the holes between them. So why are anions normally larger? Remember when we were back talking about periodic trends that anions are going to end up with a weaker effective nuclear charge because of the addition of extra electrons? Okay, so normally we're going to have larger anions, smaller cations, with the anions, think of the anions all put in there and then the cations shoved in the little corners in between. So it's going to look something like this. So if this was a representation of NaCl, then the littler ones are likely going to be the Na, and the bigger ones will be the chlorines. And this arrangement of ions in an ionic crystal make the ionic crystals very brittle. You could imagine if you were to hit along one of these lines here, I don't know where. So if I take a hammer or something and slam it right there, it's going to kind of crack along this midline, breaking apart. This is not true, say, for example, of a metal. But ionic crystals, because of this structure, they'll kind of break into pieces. All right, next up is molecular crystals. Molecular crystals are solids composed of covalently bonded molecules. Okay, so the molecules are covalently bonded to itself. The individual molecules are then held together with intermolecular forces to form the molecular solid or crystal. So I guess we could use an example here. Let's say we have some water molecules, H2O, floating around, and we freeze it. So now we have a water crystal, right, ice. So here's my H2Os. And these are covalent bonds. Each individual water molecule is then lightly bonded by intermolecular forces, which are weak. We'll talk about that in future. And that whole thing together will make our ice cube. So there's our ice cube. So different than the ionic crystal where each individual atom or ion is held together into one big structure. In this case, the molecules, the atoms are bonded covalently to each other, and then the molecules are then lightly bonded, you could think of it, with intermolecular forces. Because the IMFs are weak forces, the intermolecular forces, molecular crystals are weak. That's why they end up with very low melting points and boiling points. And then we have another type of crystal that is also made up of covalently bonded atoms. And this is called covalent crystals or covalent network crystals or network crystals. Okay. This time, the whole solid is composed of covalently bonded atoms. Picture ionic crystal, where the atoms in the ionic crystal are all of the ions are ionically bonded. Here we have a solid where all of the atoms are covalently bonded. Okay, and even though it's covalently bonded, this type of crystal is one giant molecule. Unlike the ice, where we had the water molecules, individual molecules lightly bonded together, in this case, in a covalent network crystal, all the atoms are covalently bonded together into one giant molecule. Okay, and this will make the covalent network, very strong compared to a molecular crystal. And it's actually very strong compared to a ionic crystal. Things that make up covalent crystals or covalent network crystals are actually have higher melting and boiling points than ionic crystals. Okay, so when do atoms form covalent crystals versus molecular crystals? Molecular crystals are actually a lot more common as far as covalent solids go. So basically it's just atoms that can form 4 bonds are the only ones that can form covalent crystals. Most commonly it would be carbon and silicon. And the last type of crystal and the last slide of the lecture is metallic crystals, which really we sort of talked about with metallic bonds. A metallic crystal is made up of closely packed metal atoms surrounded by a sea of electrons. And then we have something called metal alloys. What that means is you're going to have smaller metal atoms fill in the gaps between larger metal atoms in a metallic crystal. What would that look like? It'd look very similar to an ionic crystal. So you might have something like titanium and I don't know what, gold. Gold is big, right? So we've got gold. We'll make gold yellow. So we've got these gold atoms. Okay. And then interspersed in there would be, I don't know, titanium atoms, which are much smaller, kind of filling in the little gaps. And that is a metal alloy. Okay, that was a long one. A lot of information here. You kind of got to know this stuff, know the characteristics, the differences between the bonds, and that's it for today. Have a good one.